Oh, cool. It started doing that weird mouse sticking thing again that it was doing for a while. All right. Come on, mouse. Oh my God. Oh my God. Oh my God. It's that little speaker window thing. Oh my God. No, that is not what I wanted to do. No waiting room. No. Oh my God. I'm going to lose my mind today. Further. Oh my God. Stop. Okay. Where's this freaking mouse? What is this? None of that. Is that it? Oh my God, what are you doing, Mom? Still doing it. Yep, still doing it. Cool. Yeah, you're stupid. You think this is a new mouse. Oh, what do you know? It worked. Okay. While people are joining, I will be right back. And I'm going to see about reading some math books. Okay. Well, you see, I'm thinking of writing my own math book for this class. And before I throw away a bunch of materials that honestly, some of these are just so simplistic, you'd probably be offended if I showed you. It's like, oh, circle the cats in the thing. I'm like, no, God, no, I'm not going to show that to an adult. Why would I do this? But I figured I would have, some random other ways of doing things. Yeah, fun. Could be fun. Okay. So, hi guys, who's joined up as Orlando? Do I have an Orlando? What's happening right now? Yeah, I guess I should actually, have the attendance thing pulled up. There we go. Okay. And there. Okay. And it disappeared. All right. Well, now I'm even more curious. I'm sure it's somebody using someone else's phone. Stop sending me photos. I have to be a teacher. Okay. So, you guys have a fun couple of days? Yeah? Exciting? Everybody's having fun? Everybody's happy? Yeah. Yeah, cool.
So much fun.
So much fun. Everybody's excited. Oh my God.
Every day.
Yeah. Yeah, I showed up here today so they asked me to help them clear out some old math materials. And, unsurprisingly, I'm the one they don't always know all the math stuff. So I'm like, okay, yeah, sure. I'll look through it and see what we can toss, what we don't. I walk in and it's somebody's last day and everybody's standing in a circle and talking to each other. And I am just, oh my God, I got the anxiety problems and everything. And you just walk into something like that. Oh God, what's happening right now? What's happening? Oh God. And Angela's like, oh, we're waiting for you. And I'm like, oh God, no, what's happening? This is the worst. This is by far the worst ever day. But no, somebody was just, second to last day. Like, cool. All right, that's fine. I'm happy for you. You get a little party. I'm here for math. Don't mind me. I exist. Okay. Get rid of that. Nobody has their cameras on, and I am not surprised because if I was joining this, I wouldn't either. Okay. So tonight, I love this meme. This made me laugh. Not much makes me laugh out loud. This did. But we'll review the multiplying and dividing decimals, and then we'll do the whole exponents thing again. And that mouse is moving on its own, isn't it? All right, that's cool. All right. It's because I had to plug it in awkwardly because it was plugged into the monitor and it was doing that weird freezing every 5 seconds thing. I think I have a USB extension. Wonder if they have those. All right, whatever. So let's jump into stuff. Gonna do some more decimal stuff that is, of course, reviewing from last time. And then we will have fun with exponents again. I know everybody was kind of lost at the end of the last class, and that's fine because we're going to do the whole thing again from scratch. I just changed the problems around and there we go. We got new problems this time for that. So even though I covered a little bit of it last time, we're just going to act like we're starting fresh this time. Not going to pretend it's review. So when it comes to operations with decimals, we don't have any problems for this today, but remember adding and subtracting with decimals, you just line it up at the decimal point and line up your answer's decimal point right along with it and add like you normally would. When it comes to multiplying, that's when we have to have a little bit more fun. We end up putting the numbers on top of one another. We don't care where the decimal points are, because at the very end, that's when you look at it and say, okay, how many decimal places are in each one? You take that, you add them together, and that's how many decimal places your answer has. At grandma's funeral, my stomach grumbles, my grandma. I have no regrets on that. I miss my grandma. And she did always feed me whenever I needed food. Whenever I didn't need food, I guess I should say. That's what grandmas are for, feeding you randomly. My mom does the same thing. I've been asleep and she's woken me up and at like 11 p.m. asked me if I'm hungry. That's what happens. The answer is always no, but you know, one of these days you might pull it off. I don't know. All right. So hey, we got these multiplying together. And remember, a good strategy is whichever one has the least amount of digits, that's the one we're going to put second. So this one over here, even though it's simple looking, you know, it's a bunch of ones, it has 3 digits, whereas this one has 2. So we're going to lead with this guy. So it's going to be 11.1 on top times 7.3 on the bottom. I don't really care about making sure everything's aligned nicely because it's all going to come together nicely at the end, right? So it's not going to be the end of the world. So, all right. So first off, we're going to take this 3, multiply it through there. Here's a hysterical hint. What's 3 times all of these ones? A bunch of 3s. There we go. There's that line. Did I do this intentionally? Maybe. I mean, we got the idea, right? So, I mean, we didn't need a horribly hard one for starting off the day. No computing pi this class, I promise.
I appreciate it.
Yes. And the next time I decide to do something that insane, I'm just going to be quiet until I have it already planned out. That way it doesn't look quite as horrifying. Ibuprofen, yeah. Don't worry, if you ever need ibuprofen, if I give you a headache, I do in fact have a bottle. All right. Then the next digit, we put a 0, and guess what 7 times all those 1 is? 7, 7, 7. Okay, cool. And then we just add these together. There's going to be a lot of 1s to be carried. There's a 3. 3 and 7 is 10. Okay, and then we carry that one. 3 and 7 is 10, plus that other one is 11. So I carry that one, and we have an 8. The main thing to take away when you're multiplying numbers with decimals is where the decimal point is going to be at the end. So as long as you can multiply these numbers together, whoop-de-doo. As long as you can get where the decimal place is going to be at the end, those are the 2 main concepts. Even if you do a problem and you're like, oh God, what happened? That's okay. If it's a hard one, as long as you understand the core concepts, you're fine. So yeah, you look at this, say how many digits are after the decimal? 1. How many here? 1. 1 and 1 is 2. So we put it, so we have 2 numbers after the decimal place. And yeah, that seems about right. 7 and change times 11 and change would be a little higher than 77, right? So there we go. Not too shabby. Let's look at the next one. I only have 3 for multiplying. I don't remember how many I have for dividing. Hopefully 3. Yeah, just 3 and 3. So it's not going to be too bad. Just a little review. All right. So speaking of, oh my God, this isn't the worst problem I've ever had to do. We got 0.5 times 0.25. All right. So this one has 1 digit that we care about, and this one has 2 digits that we care about. So that one's going to be on top. and we'll multiply by 0.5. And again, I don't care that these aren't lined up because we're doing multiplication. All right, so all we do is 5 times those guys. 5 times 5, 25, carry the 2. 5 times 2 is 10, plus 2 is 12. Nothing's going to happen over here. So, I mean, in terms of carrying, I'd be carrying to add a 1 to a 0. So, and just put that right there. And I don't care to go down a line because our next digit is 0. 0 times all of that is just going to poof. So we're done. All we got to do is figure out where our decimal point is, which you look at the places after the decimal point. On our top line, we got 2 digits after the decimal. On the top, on the bottom, we got 1 digit after the decimal. Add those together, we get 3 digits after the decimal. That's all we got, right? So you would put it, so we have 3 digits after that decimal place. And generally you want to put a 0, like a kind of a placeholder 0 there. If you don't, it depends on your teacher. You might get marked down, you might not, because technically it's not correct without that 0, but I mean, we know what it means. If anybody's telling you they don't know what it means, they're a liar. Oh, and it's unlikely that you'll run into it, but if you ever do a problem like this and you end up with like 4 digits that you have to have after the decimal place and your answer only has 3, then you'd go over 4 anyway, and you'd put a 0 to kind of bridge that gap. I can't think of any particular, you know, I'm not magic with decimals. I just know how to do them. So I can't think of anything off the top of my head that'll do that. Oh, wait, this one. I actually wildly made up this problem this morning. I set all this up about 8 hours ago, I want to say. So, yeah. It's like, this looks like a good example. This will cover something that I probably haven't thought of talking about. And what do you know? It just came up. Look at that. This one is hysterically easy, right? Because both of them, all we really care about is one of these digits. We see a 5 and we see a 3. We know there's going to be a 15 in there somewhere, right? All right, so since each one only has 1 digit that we care about in terms of multiplication, it doesn't matter which one you put on top. I'm going to do this one just so I can show you that, hey, sometimes it's going to look stupid. You know, we got the bottom one kind of hanging off further, but I mean, end of the day, it doesn't matter, because all that really matters is these 2 numbers right here. And well, what do we get? We have 3 times 5, it's 15. We don't have anything else coming from this. I don't have 0 multiplied by that 5 or 3 times all of these zeros. I don't have to worry about that. All that matters here is the 3 and the 5. But we also have to worry about where the decimal is going to be. So you have to think, okay, well, after the decimal place on this top one, there's 3 places, right? You know, that's when those zeros actually matter is, you know, how far over is that 5? That's 3 digits. And then down here, that's 4 digits. So we have 3 and 4. That means that this guy has to be 7 digits down. So the easiest way to do that, because that's honestly, you know, you don't want to add too much guesstimation on how many zeros you're going to end up having. Just put your decimal at the end and just move it that many times. 1, 2, 3, 4, 5, 6, 7. That's where that's going to be. And every time you make that little jump, just think, oh, if I put that decimal here and I have to have a 0 here, what's going on in between? Just a bunch of zeros, yeah. So every time you have that little jump, there's a 0, there's a 0, there, and there. And if it's too hideous for you, because it's kind of making me cross-eyed, you can absolutely rewrite it if you want to. But as long as you cover, hey, 3 digits, 4 digits, okay, then our answer has to be 7 digits out, then we're good. Now you might look at that and say, oh God, why would we have that many zeros? Well, if we make it that far, we'll have a nicer way of actually writing that at the end of this class in scientific notation, which is the very end of the exponent unit. Are we going to make it that far? I don't know, probably not. But I can hope. I could certainly hope. All right. So that's multiplying decimals. Now we have dividing decimals. Now this is kind of interesting because I was bored earlier, so I made up a way of doing it. So my first paragraph here is literally just, I'm pretty sure it'll work. I made it up on the fly. It's a cheap, quick method of that I made up. You can multiply both numbers by 10 until you have nothing but integers, and then reduce down. So if you have like 452 divided by 536, that'll reduce to 113 over 134. And then you could do long division out of that. And that would work. That would work 100%. And then you could even, if it ended up having a higher numerator, for instance, you could turn it into, clean it up, turn it into a mixed fraction, and then just do long division with the remainder and just slap that on as a decimal. It's wildly cheap, but it would work. In a pinch, it would work. Am I insane? Yes. Should I have really talked about that? Do we need to randomly do that? Probably not. But I could show you it working. But otherwise, when it comes to dividing decimals, you're going to do long division at one point or another. I mean, if you're doing it on paper, you're going to do long division at one point or another. And the nicest way to do it is you move the decimals to the right on both the dividend and the divisor. Remember, dividend is what's being divided. Divisor is what you're dividing by. Move the decimal place to the right as far as you have to so that the divisor doesn't have any decimals left. It's just an integer at that point. So as long as that ends up being an integer, we don't care about the dividend being an integer. And then you just do long division from that, wherever the decimal is in the dividend. So the thing you're dividing by, wherever the decimal is on that, you're going to move the decimal straight up, and that's where it is in your answer. So most of the tricky bit with long division of decimals really is just not losing where the decimal is going to be. That's it. Otherwise, it's long division as normal. So other than the long division we did originally, it's the same concept. You just have to move the decimal around. That's it. So let's do some of that. Woo, look at that. Isn't it beautiful? Google review for a courthouse. I found this earlier. It's just a screenshot. Candy bowl only had inferior types of candy, 1 star. What do you think that is? That those, you know, are we talking dum-dums? Because dum-dums are good. I don't care what anybody says. They're the cheapest candy you can get. They're wonderful. Part of the screen was missing when I was reading that. Did anybody else have that problem where part of the screen was missing when I was reading out the last slide? And in fact, when I don't have it under the slideshow, are you able to see it? Like, do you guys see the whole thing now? Okay. Interesting. Interesting. Here's a crazy idea. How about now? You guys see the whole thing now? You have like a little black square and 2 giant black squares in the middle. Aha. Okay, so I'm figuring out what that is. Essentially, So since I have it screen sharing, if I move either the participant window or the chat window over it, because those are set as always on top, it's just going to show you a black screen because it's only showing you the web browser window. So I'm going to be very conscious of making sure that those windows don't cover anything important. So if that happens again, chances are whatever's under it, you don't care. And if it is something you care about, yell at me and I will make it work. There we go. Cool. All right. So I'm going to write these guys out real quick. I'm just going to write the first one. We're just going to write the first one to see how much room we got on the paper. Okay. So number one, we have it set up pretty nicely, right? Because the guy that's being divided, which is the dividend, and that one's good anyway. But the divisor right here doesn't have any decimals in it. And if it doesn't have any decimals in it, then I don't have to shift things around. I don't have to shift things around at all. So we can just start doing long division. Now, the only important thing, well, other than not making horrible mistakes, which it's entirely possible I'll make horrible mistakes tonight. So again, if I make a stupid mistake like I did last time, just yell at me. I'm good at making stupid mistakes. So the important bit when you're doing long division with decimals is that wherever the decimal is in the dividend, it goes straight up. That's where that's going to be in your answer. So it always goes just straight up from there. Then we just do long division as always. We look at the 31 and the first two digits here, 31 going into 45. Yeah, that happens once, right? So multiply that, we get 31, and we're going to subtract that line. We now end up with 14, which 31 wouldn't go into. So we have to pull down the next digit, which makes sense because, hey, that's the digit we'll be at. And we say, okay, how many times will 31 go into 148? Which is about 4, right? Okay. So we have 4 times 31. So that gives us 124. We do our subtraction again. And then when we do that, we have 24 right here, which again, 31 wouldn't go into. If it did, that would be my big, bells going off. I made a mistake in the last step, which totally happened last time when for some reason I was so out of it. I said that 15 didn't go out of 20. Good times, good times. I feel like if my brain starts deteriorating like it did last time, I'll probably just cancel. I think everybody would prefer me not rambling to me rambling. All right, so 31 going into 248. Goes in 8 times evenly. That's 248. So we do that subtraction. We have 0 remainder, which means our answer is exactly 14.8. Not bad. It's a nice little problem. It's an excellent example of long division. Only had a couple of steps. I didn't torture you. There's only one of these that might torture you. So the next one is going to be 16.06 divided by 2.2. Okay. So this one does have the thing where the divisor has a decimal, right? So before we can even start, we have to move that decimal one to the right to make sure that our divisor stays an integer. We're going to do the same thing to the dividend. We have to do it the same way on both of these. So we end up with 160.6 divided by 22. If I had to guesstimate on that guy, I'd say it's probably going to be a bit less than 8. 16 divided by 2 is 8, so 160 divided by 22, it's going to be a bit less. All right. So exact same thing. Remember, the decimal goes straight up. Now 22 won't go into the first 2 digits, so we have to look at that whole thing overall. Like I said, probably 7, right? So 7 times 22 is 154. Do your subtraction, we get a 6. We bring down our next digit, which is also a 6. Oh my God, look at that. That goes in perfectly. 3 times. We get 66 down here and 0 for the remainder. And there's a smudge on my glasses and I'm losing my mind. There we go. 100% cotton shirt. Very good for glasses. All right. So they end up scratched to all hell, which always happens. All right. Now the one that nobody's gonna like. I have 413.7375 divided by 4.125. Hideous, right? We got 7 digits being divided by 4 digits. Not nice, not nice at all. But doesn't matter how nice it is, it follows the exact same concepts that we have learned already. So at the end of the day, it's just a number divided by a number. So we move this decimal over until that's an integer. We move this decimal over the exact same amount of times, which was 3. So now we have 413,737.5. So 413,000, beautiful, divided by 4,125. I'm sorry, guys. Huh? Yeah. I think I actually just slapped the keyboard. And then I put decimals in between at places that I just kind of felt like. I mean, really, when it comes to this stuff, I mean, that's the easiest way to make good long division problems. If it doesn't go in evenly, if I'm just slapping that keyboard, it's probably not going to give me anything nice. You know, a fun thing is one of the reasons that you end up seeing colleges go through edition after edition after edition of different math books, and you want to say it's a scam because it kind of smells like a scam. But really, I have proven the book wrong so many times. And then you can, like, some of these publishers are nice and they'll actually give you money if you find it. When they're not nice, I don't even tell them. Because that's just going to make everybody have to set that up again. But yeah, you know who makes all the practice problems in your books? Grad students. It's always grad students. It's never the professors who get tons of money. It's always freaking grad students. And that's why you end up with so many mistakes. But then again, I have a degree in this stuff and I still make plenty of mistakes. So whatever. All right. So first four digits to first four digits, 4125 to 4137. Oh yeah, that's a one. That's a nice one. Look at that. We've already moved over to the fourth digit. That's great. 4125, we do our subtraction. We end up with a 12. We bring down the next digit, that's a 3. Oh, but you know, 4125, does that go into 123? No, no, it does not. So we can move on to the next one. We bring down the 7. Does 4125 go into that number? No, no, it does not. No, it does not. Okay. Well, how about 12,375? What about that one? Exactly 3 times. I lied, I didn't slap the keyboard. I wanted to scare everybody. I'm a little cruel sometimes, but it's fun. So 3 times that is 12,375. Look at that. Okay. Look at that, where I don't smudge it and have. Okay, I don't have blue on this side of my hand. Where did it go? All right. That's cool. That's a 4. That's a line. There we go. Yeah, not bad, not bad. That was less steps than our first one, right? Cool. Everybody having fun with this stuff? We're good with it. We feel better. We're happy with this stuff. We can move on before 7 p.m. Yeah. I like it when that comes together. Okay. Well, if you were here at the very end of the last class, this will look familiar, but exponents. Exponents. We're going to go back over the whole freaking thing because you know what? You only got 15 minutes to wet your feet on this. That wasn't enough. Is that too blinding over there?
No.
Nah, we're killing it. We're killing it. I hate when that happens. Better?
Yes, thank you.
No, it's killing sun. I'm a nerd. I have an aversion to light anyway. All right.
I like it, but not in my eyes.
Yeah, that'll do it. Cool. Yeah, no problem. All right, so exponents. They're shorthand for repeated multiplication of the same thing by itself. For instance, shorthand for multiplying 3 copies of the number 5 is shown on the right hand of the equal sign in this. 5 times 5 times 5 is 5 to the 3rd power. It literally just means, hey, I got that 5 and I got 3 of them, and they're attached to each other. They're multiplying. That's what that is. So the process of using exponents is usually called raising to a power, where the exponent is the power. So the expression 5 with the little 3 up top is pronounced 5 raised to the 3rd power, or 5 to the 3rd. And on the next guy right here, there are 2 specially named powers. To the 2nd power is generally pronounced squared, and to the 3rd power is generally pronounced cubed. So 5 with the little 3 there is 5 cubed. And if there was a 2, it'd be 5 squared, that sort of thing. So in math, you'll usually have the caret symbol. They're used to represent an exponent. The main reason I have that in there, one, because a lot of math books will have that sometimes. Sometimes you'll have to type it in if some people are using, say, I know a lot of people use like just the Google search bar as their calculator sometimes when you're, in a pinch. But you can use that symbol on a keyboard, or if your calculator has that button, to represent an exponent. So you would hit the first number as which is the base of it, the caret symbol, then the power, and it'll spit out whatever that is. In this case, it's 125. And more annoyingly, sometimes there's just a little italic XY as the button for that, and I have no idea why. No idea why. I kind of hate that. So working them out, as you would expect, you would just multiply that number by itself that many times. So 5 cubed, you would either, punch into a calculator 5 cubed or write 5 times 5 times 5. So you can always break down a number into its prime factorization and then put it in an exponential form. So if you had 125 and you were working backwards, you would do the factor trees that we were doing before when we were doing the prime factorizations and, LCMs and GCFs and things with 3 letters. And you would do the prime factorization, and whatever numbers you have there, you just stick them together, and the exponent is how many of that factor you have. So we're going to do a few of those. We're going to break these down into exponential forms as I have written. These are different from the ones we did last class. I'm going to write those out real quick because these are not going to be a nightmare. This is the concept that we made it to at the end of the last one. So we're going to break these guys down into their exponentials. So we're just going to factor tree them all. 64 is 2 times 32, which is, 4 times 8. 4 is 2 times 2. 8 is 2 times 4. That 4 is also 2 times 2. We got 2's all the way down. We got 2's everywhere. And how you do these, again, doesn't matter. I could have started off by saying, hey, 64, I know that. That's a perfect square of 8. You could have done it as 8 and 8, and then each side of that would have looked like one of these guys. Wouldn't have mattered. Why? Because these 3 2's are the same as these 3 2's, so nobody cares. Speaking of, I just said we have 3 2's and 3 2's. How many I got? 6? 6 2's? Yeah, cool. So you write what it is, and how many of it you got is your exponent. That is 2 to the 6th power. It is a perfect power of 2. And that's it. That's all you got to do. Not too bad. This one, I don't remember what numbers I threw at it, but a nice rule of thumb is if you have something that's kind of weirdly symmetrical like that, it's usually probably going to be divisible by 11, which it is. I thought I had an 11 somewhere in there. I forgot what this was, and it's 11 times 121. Which again has that nice little symmetry, and you might say, hey, what is that? What is that? Well, it's the perfect square of 11. Cool. So 1331 is just 11 times 11 times 11. We got 11 multiplied by itself 3 times, which means we have 11 cubed. And some of them aren't as nice. This one's not a perfect power, but we can just break them down into their exponents anyway. So we got 4410, 4,410. we could do whatever we want to this. We could say this is 10 times 441 for all we care, right? We can do that. The 10 turns into a 2 and a 5, and I've already chopped off one of the digits from this guy. So 441. I don't know what that is, but it's odd. And if it's odd, I'm going to try a 3. Yep. It's divisible by 3, and it goes in 147 times. 147. It's a weird odd number. You might try a 3. And it works. It's a 3 and 49. You might recognize that as the perfect square of 7. Otherwise, you would stumble upon that by trying different odd numbers. So that one's 7 times 7. So we got a lot of different factors to keep track of, right? So one way to do these when you have a lot to keep track of is just write out which factors we have. We have 2s, we have 3s, we have 5s, and we have 7s, right? And all of these are going to be multiplied together with their powers. So I'm just going to kind of put the multiplication symbols in between those, right? All right. So then all we got to do is count how many of each we got. For this 2, how many we got? Just 1. So I don't need to put an exponent on there. Anything to the first power is itself. 2 to the 1 is 2. 500 to the 1 is 500, etc. So you don't really ever have to put a little 1 there. Sometimes you do just to make your life a little easier when you're doing math with exponents, but right now we don't care. The 3, we got 2 of those. So we put a 2 up there. That's the power on 3. We only have 1 of the 5s. So again, we're going to leave that alone. And then 7, we also have 2. So we make that a 7 squared. So all this is just saying how many of those factors these guys have, right? Because this is 2 times 3 times 3 times 5 times 7 times 7. Not too bad, right? So let's look at some other problems. The other problems I have are just go the other way around. Let me write them out real quick. Was there a weird yellow box around that? Whatever. So there's our 6, 7, 8, and 9 problems. And I cram those all together because that's how much room I'm going to need. So as you can expect, this is going to be so hard. Oh, God. Now, let's focus that. Okay. All you have to do with these is you have this number 6. We have 7 to the second power. All we're doing is we're breaking these back into numbers, right? So if you know that the square of 7 is 49, that's it, right? Now, if, for instance, it's something that you don't know, you might not know 4 cubed, right? 4 cubed means you have 4 times 4 times 4, right? Well, we know 4 times 4, right? That's 16. We're used to that one. That one pops up all the time. 4 times 4 is 16, so it's 16 times 4. That one, 64. See that? 64 came back. Look at that. Because here we had 6 2s. Now we had 3 4s. Okay. All right. Well, now we have 2 to the 4th. What's that? Now, like I said, you might have a calculator or might have a button for that. Personally, my calculator is both old and fancy, so I can't see it in the dark like everybody else's new calculators these days. But I have this button right here. It's kind of reflecting, but right here, I got a caret button. So for me personally, for my calculator, I can hit that caret button, put the 4, and that's telling me I have 2 raised to the power of 4. Hit enter, I get 16. Now, if you don't have a calculator that can do that, you can absolutely still break it down. And you would be fine because 2 times 2, 4 times 2, 8 times 2, 16. Now, this last one, if you haven't ever run into something that's an exponential form like this, when they're bunched up next to each other like that, that implies that they're being multiplied. Okay? That's what that implies. Those 2 numbers are being multiplied together. So what that particularly means is that you have 3 4s, 4 2s, all multiplied together, right? The whole thing. Now, I made this one a little easier for, the purposes of our examples because what's that? 64. What's that? 16. So this guy's going to be the same as 64 times 16. So we get 1024. Which is 2 to the 10th. Which is why when somebody asks you how many megabytes are in a gigabyte, the answer is never 1,000, it's 1,024. And that's why when you buy a hard drive at like Best Buy and plug it into your computer, it has less space than they said because they were counting by 1,000. Sucks to be you. Gotta love it. So you lose 2.4% of whatever they're talking about. So how do we feel on these? Are we feeling good about understanding what an exponent is? We're ready to push on to actually using them? Because we're going to start using them. We're not done with exponents by a long shot. Nobody's freaking out. Cool. So now, we already kind of saw a little bit of it, but multiplying exponents. Now, these are a little bit more interesting because this only applies to ones that have the same base. That last one we did, that was 4 cubed times 2 to the 4th. That one we couldn't have done with this because the rule here only applies when they have the same base. Only. Like I have down there on the last line, if the terms didn't have the same base, you would have to work them out separately and multiply them together, just like what we just did in the last example. But the nice thing is that think about what that last example showed you. We had 4 cubed and 2 to the 4th. So we wrote out 3 4s and 4 2s. Well, what happens if I have 3 cubed times 3 to the 4th? That means I'd be writing out 3 3s and then 4 3s, right? So how many 3s altogether are being multiplied together? 7, right? Because you're just mashing them all together. And that's actually what ends up happening. If you have 2 exponential numbers that have the same base and you're multiplying together, what you can do is just add the powers together. So there's 3 of them multiplied by 4 of them, so you have a total of 7 of them. So 3 cubed times 3 to the 4th is 3 to the 7th. It's not too bad. Not too bad.
So you don't multiply them, you just change the.
Yeah, you just change the exponent. That's it. You don't have to multiply anything. You just add the powers. And you can actually make, I was kind of a wizard with this stuff. At one point when I was tutoring, the kid went into the army. I don't know why his brain worked this way, but he referred to me as Ben, protector of all math realms. And I was like, dude, what? I don't get it. I don't get it. But I could fill an entire board with like one gigantic, horrifying algebraic expression like this. Because this is actually, that's where stuff like this is going to go, is you'll end up having to simplify something like a to the 5th, b to the 3rd, c to the 10th over a to the 2nd, b to the 5th, etc. And by the rules that we're going to cover tonight, even though it might sound complicated, you'd be able to do it in one step. And then you look like a wizard because it looks like it's more complicated than it is. Most of this stuff with exponents looks like it's more complicated than it is. That's the nice thing. So let's do some of these. Medium, what's pineapple on pizza? Guy named Pizza. Pineapple on head. This was the dumbest thing I found on the internet today. I decided to grace you all with its presence. I saw it, and it actually made me chuckle a little bit because it's just so profoundly stupid of a joke that it's like it wrapped around and became funny. It's like watching Mystery Science Theater 3000. It's awful, but that's the point, is that you can laugh at it. Okay, so these ones, we're just going to multiply and leave them as exponents. Okay, guys, put on your thinking caps. I got 2 to the 3rd times 2 to the 6th. What's the answer? For those of you who will type it in chat, you might find that little caret guy being attached on the number 6 on your keyboard. If you're using a keyboard. If not, then, whatever. I don't know if you guys are on tablets or Android or whatever. Yeah, exactly. We have an answer. So all you got to do, add the powers together. What's 3 and 6? 9. Oh my God, exponents are so hard. Look at that. Oh my God. Oh my God, that was so awful. Number 2, we got 5 squared multiplied by 25, and we want this thing to be an exponential form. So we're multiplying these 2 numbers together. Well, that's easy, right? Because what is 25? 5 squared, right? It's 5 times 5. So that thing is 5 squared. So if I'm multiplying those 2 things together, I got 2 5s times 2 5s. How many 5s I got? Everybody better have said 4. Even if you said it to yourself. I don't know how many of you are paying attention. At least 2 or 3 of you. I don't know. God, you couldn't pay me to listen to somebody like me ramble on for 2.5 hours at a time. I can't stand myself. I don't know what you guys are doing. All right. Aha, how about this guy? This guy, we have 3 cubed times 2 squared times 3. Well, that guy doesn't have the same base as everything else, right? And if they don't have the same base, it doesn't apply to that rule. it's kind of on its own. Only the things that have the same base can go together. So if I'm multiplying this stuff together and I'm supposed to leave everything in exponents, all that can really go together is this 3 cubed and this 3. This guy's just going to hang out till the end. So this is where I said, hey, you don't have to put the first power, but it might help you. How many 3s do I have right there? 1. So you can write that if it makes it easier on you guys when you're doing like homework and what have you, when you're prepping. It absolutely could come in handy right here, because then you could think, hey, I got 3 of these multiplied by 1 of these. I got 4 of them total, right? 3 plus 1, 4. What do I do with that 2 squared? Well, you could put the multiplication symbol between them. I prefer not to, because technically that implies multiplication, and that's the nicer way to write it. It's just not pretty. Well, it's not pretty if you haven't, done 1,000 of these. It's prettier to me, whatever. That's also, another thing with math books. What is the answer? Whichever way is prettiest. That is like a universal rule of math stuff. I don't care who's live on Twitch. I'm teaching. Okay. 4. I have it written. I'm going to write it on this paper the same way I have it written in here. That thing. Well, remember the caret is just implying that that's the power on that number, right? So this really is 7 squared times 7 to the 5th. Now you might notice that I just dropped those parentheses. You might say, hey, Ben, why did you drop those parentheses? Because they don't actually matter. What's happening between these sets of parentheses implies multiplication. If I have something outside of a set of parentheses, it means that whatever's outside of it is multiplying against that set of parentheses. But in each one of these sets, I have one thing, just a thing. It's 7 squared, right? So I don't have to put that in parentheses. Do I need to go around and write the number 1 and then just put it in parentheses? No, you don't need to do that. In fact, brackets, parentheses, or brackets, whatever. Technically, that's correct. That's a 1. You don't like looking at it because writing it that way is stupid, right? That's horribly stupid. You don't need that. So why bother? I have one thing in a set of parentheses. Do I need to write it as being in parentheses? No. As long as I write it in such a way that it implies that these 2 numbers are multiplied, we are good. This means the same thing as this. And one nice way of writing it could be writing it with one of them, the second one in parentheses, because then I can still see that's multiplying onto that. Doesn't matter. It's all the exact same thing. There is 4 ways of writing this exact same problem. Which way is more correct? None of them. They're all the same. Does it matter? As long as you can recognize that these guys are the same. That's why I wanted to push for this particular problem. As long as you recognize this, is this, is this, is this, then we are good. Doesn't matter how you write it, matters what the end result is. I got 2 of them times 5 of them, which means I add those powers. What's 2 and 5? 7. Got 7 to the 7. What is 7 to the 7? I don't know. I'm kind of curious. 823,543. I would rather write 7 to the 7th. Which actually helps out a lot when I'm tutoring people in higher level math, say, you know, trig or college algebra, I would constantly be asked, do I leave this as an exponent or do I have to multiply it out and figure out what it is? And I'll look at them and be like, how easy would it be to break that down? It'll take me a little bit. Cool, leave it as an exponent. How easy would it be to break it down? Really easy. Okay, cool. Then break it down. That's really what it ends up being. Okay, not bad, not bad. Let's hit some more rules. Let's hit some more rules. Am I gonna run out of stuff tonight? No, okay. I still got scientific notation in there. This isn't too bad, right? It's not too bad. Even division. We're gonna do division of these now. It's not bad at all. It's actually easy as hell. I'm pretty tempted to make up a problem for this, and you know, after last class, I probably shouldn't have that impulse anymore. But I'm probably still going to. All right. So division, 2 to the 5th divided by 2 squared is our example for this one. So in matters of dividing exponential numbers with the same base, it's simple. You keep the same base, but you subtract the bottom power from the top power. So just kind of like how multiplying these guys ended up with adding the powers, dividing them ends up subtracting the powers. And I'll even show you that visually. So you can see that 2 to the 5th and 2 squared on bottom, right? Essentially, we have 2 to the 5th divided by 2 squared. And I want to show you guys how this works, right? So like I've said before, division and fractions are the same thing, right? Because with fractions, the top part is basically being divided by the bottom part. So if I write this as a fraction, we essentially have something like that. Now, if you're stuck on a test and you're like, oh God, I don't remember what it is, do I do? Do I divide them? Do I subtract them? What do I do? Well, watch what happens. If I have 2 to the 5th, I already regret this particular problem being on there, but you know, I'm already writing out too many 2's. You basically have that many 2's over that many 2's. Well, when we were doing fractions, what happens when you have the same factor on top and bottom? Cancel out, yeah, 2 divided by 2. What's 2 divided by 2? 1. Okay. Okay, 2 divided by 2, what's that? 1. Oh, cool. How many do I have left? I have 3 on top, right? That works out in that subtracting these powers ends up being shorthand for canceling them out, like this. Same as adding the powers was kind of shorthand for that funky multiplication that we had going on, right? So that's how this ends up working. It's essentially canceling. So if the world blows up, you don't know what to do, you can write out the whole thing and cancel stuff. I don't recommend it. It's going to get ugly, but you can. All right. So now we got some examples and a random meme with Terry Crews in it. That is a screen cap of Brooklyn Nine-Nine, which is one of the best shows ever, and everyone should watch it. Also, Terry Crews is an American treasure. I will die on that hill. I'm just writing these out real quick because, like the last ones, these aren't going to take us very long. Okay. So here's our pile of example. It's a nice pile of example. I like them. You like them, whether you like it or not. I have decreed it. Number one, stupid easy, right? We have 8 cubed divided by 8 to the first. You might say, Ben, why are you using the slash instead of the division symbol? One, it's easier for me to type, so I might as well write it that way. But on top of that, again, it's the same as a fraction. And I actually am very, very used to writing these as fractions. This is how I usually will run into these types of problems. When you're learning it initially, yeah, you'll see them with the division symbol between them. But in higher level math and college algebra, you're going to see them as fractions most of the time. So you can view me writing it this way as being kind of both at the same time, it's the same thing. So all we got to do, we have 8 cubed divided by 8 to the first. So what we're going to do is we're going to subtract those powers. What they're dividing by is being subtracted. 8 squared. This is one of those ones where students would tell me, hey, how do I want to write this? Do I write this as 64 or do I leave this as 8 squared? Again, doesn't always matter. Did I specify? Nope. I never write instructions on any of mine. I don't know why I try. So problem like this, it's easy to say it's 64. So if you were working it out, you might say it's 64. Again, doesn't matter. On these ones. Huh?
What was that as subtraction?
Well, you can see this kind of slash. That's saying that this is being divided by that. So as a fraction, you would just have that one on top. So all of these are essentially top divided by bottom. So if you write these as fractions, you're going to end up seeing this sort of thing happen. And then same thing. If I'm dividing fractions of these guys, I have the same base. What am I going to do? Subtract, right? So we just do that top power minus the bottom power or the divisor's power, however you want to look at it. Dividend and divisor is entirely reasonable thing that I hate having to remember which is which. I'm not going to lie. I hate the vocab of this stuff, so you guys probably really hate it. Cool. Well, 8 minus 14 or 18 minus 14, 4. 2 to the 4th. Again, you could multiply it out. It'd be a 16. I'm going to leave them as exponential because, hey, what are we learning right now? Exponents.
So for multiplications, you add them. For divisions, you subtract.
As long as they have the same base. If they don't have the same base, they don't go together. And that's why number 4 is over here. Number 5 or number 3 with the 5s. That one I wrote as a nice example of, hey, you know how I told you if you're in a test and you're in a pinch and you might just have to write them all out. You're not going to do that to that one, right? It's 106 5s being divided by 92 5s. It's a lot of 5s, right? I mean, you could think of it as a fraction, and you would have that. And if you visualize that, you can kind of remember, hey, they're kind of canceling out. Every one here will cancel one here, and it'll go on and on and on until you don't have any left, right? Okay. And that ends up breaking down to just subtracting them. It's easier that way, right? So how many 5s do we got? 14. Nice. Not horrible. And yes, I wrote this next one in kind of a horrible way of looking at these, but there's a reason for that. Now, the reason that I wrote these in this particular way is because if I had, and you don't have to write these in your notes, so don't worry about this. If I had something that looked like that, in the order of operations, you would go left to right, right? This times this, which is fine, divided by this, and then times that. It would break. It would actually break because you would end up multiplying this 3 to the 4th. That would bring it onto the other side of the division symbol. It would actually break. So these have to be sectioned off to say, hey, this multiplication has to happen first. So that's what's happening with these brackets down here. The brackets, I know a lot of people tend to get scared when they start seeing brackets. Brackets are basically, hey, this is another set of parentheses, but you don't want to get it confused with the other set that's hanging out there already. So they put brackets on them to, separate it out. So you can kind of see this as a set of parentheses just because there's another one already there. But these guys are multiplied anyway, right? So you could write that this way if you wanted to. Likewise, I could do it that way. So you could kind of see it. You could kind of see it as being, if one's being divided by another, you could see it as a fraction. You could do it that way. Because what ends up happening is this division symbol basically means that you have that same thing happening like over here, like over here, like over here, to both the 2s and the 3s. Kind of separately, just with that symbol right between them. So it actually is a little bit easier to understand if you write it as a fraction, right? Because then you can kind of see, hey, I'm going to look at that part, and then I'm going to look at that part, right? So you do them kind of separately. What you're going to end up doing is you're going to end up writing it as 2. So our first number here, our first factor. And then we do the top power minus the bottom power. Well, we don't have a number there. So again, this is where I say that if you need to, you can put a 1 on something that doesn't have a power. And notice that if I didn't have that multiplication symbol there, I totally could have seen this as a 23 to the 4th power. That would have really messed us up. So being able to just recognize that we have 2 different numbers there, that's what that was there for. So we do the 2, and then the top power minus the bottom power. 3 minus 1. Now this, since all of these guys are kind of mishmashed together, this is actually just going to stay multiplication. Because of the multiplication that's happening between this 2 and 3 right here, and the 2 and 3 down here. So then we do the other number, the other base, we have a 3, and we do its top power minus its bottom power. So we have something like that. Now, my question to you is, would you be able to get this from how it's originally written? Yeah, you might go a little cross-eyed, right? Might go a little cross-eyed. And I'm not gonna lie, I would go cross-eyed. If somebody threw that in front of me and said, don't rewrite that, just do it, give me the answer. I wouldn't like that, right? So sometimes reframing the problem comes in really handy, because this is a whole lot easier to understand than that, right? Whole lot. So if you can, just reframe it, and you can very easily just get the answer. You don't even necessarily even need to write this step. You could just be like, oh yeah, 2. What do I got? 3 minus 1? Cool, that's gonna be a 2. Okay, and my next number is a 3. All right, what do we got? Oh, that's gonna be 5 minus 4. Oh, then it's a 1. Okay, so I don't need to write that. So that's all I got. And this would be a perfect example of a problem where if somebody said, hey, do I want to leave it as that? Question, is that ugly? Is that stupid looking? It's kind of stupid looking, right? These are nice, neat little things. 2 squared, that's a 4. Do I want to leave something as 4 times 3? No. This is a perfect example of one that I would actually just multiply together. This whole big, ugly, hideous looking thing is a 12. Cool.
But you don't have to divide anything, everything is
Yeah.
pretty much multiplication.
There's no actual division happening there, is there? Yeah, because, well, I mean, think about it. Think about it. Let's say I did have, let's do that 2 to the 3rd over the 2 again. Let's just look at that piece, right? So what we're looking at, what we're trying to understand is what's going on with the division right now, right? Because things are being divided, but we're not actually doing real division, right? It works, but because of the way exponents work, we don't actually have to make division happen. Now, one thing you could do, if you multiplied this whole thing out, you would have an 8, right? 2 to the 3rd is 2 times 2 times 2. You end up with an 8, right? 8 divided by 2. What's that? 4, right? We get a 4, no problem. Well, let's look at it another way. Let's do 2 to the 3rd over 2, but we're gonna look at the exponents, right? Well, I got 3 2s over 1 2. I'm gonna subtract them. So that means I would have 2 of them, right? Well, what's 2 squared? 4. Now, so we end up in the same place. Division is taking place, but the division that we're doing by doing this subtraction right here is just shorthand for canceling powers. We're canceling out factors that are being repeated. So I don't want you to think too horribly hard into that, because that comes in stupid handy to wrap your head around it that way when we're doing algebra. Stupid useful. Oh my God. Like I've found people who were scrambling and freaking out, not knowing what they're doing. And I explain it that way. And they're like, oh, well, what the hell? Why am I trying to write it this way? I don't know. It's easier this way. And this is where I told you that you didn't want me to write an example, because weird things will happen. Weird things happen when I'm writing examples, right? Nobody wants to see me make it up. It gets ugly. Let's put that off to the side. Hey, look, it's a desk. Isn't it beautiful? It's beautiful. That is gigantic. That is gigantic. It is blown up like 6 feet tall in this room. All right, so let me think of some example here. Let me think of some examples. No, you're not gonna like it. I'm just gonna tell you that right now, guys. This is going to be the absolute ugliest thing you see all day. Do not be afraid. It's going to be easy. But after I do this one, that's when our break will come in. Oh my God, what the hell is that? Oh my God. Why did he do this? What is wrong with this guy? Has he had too much sugar today? The answer is no, I only had one Mountain Dew and a ton of jerky. Did I eat did I eat breakfast? Did I eat lunch? No, I'm literally just going on Mountain Dew and jerky right now. Yeah. I am not a healthy human being. Okay, so we're going to simplify this. We're going to make this not ugly. What does it mean when a book wants you to write something that's not ugly? They'll usually have the word simplify right up top. It'll just have a little period there, and you'll look at that and you'll be like, the heck, what is that supposed to do? It literally just means if there's stuff to cancel, cancel it, make it not ugly. Make it not ugly. So first point of business, what's 10 divided by 10? 1, right? So if I got a 0 here and a 0 here, so that's 64 times 10, that's 40 times 10. What's 10 divided by 10? I'm just going to make that go away right now. Cool. That's great. But wait, we did 64 already, right? Let's break these guys down into exponents. Let's break them down into exponents. So we have 64. That's, a bunch of 2s. We're going to end up breaking it down into. That's right. It's 6 of them, right? So let's rewrite this problem. We've already canceled out the zeros on that guy. We haven't even looked at this stuff over here. We haven't even looked at it. That's fine. That's completely fine. Yeah, let's write it right here. So 64, this guy on top, that's 6 2s. So we'll call it 2 to the 6th. And then I'll just rewrite all the ugly stuff there. I got 6 A's, I got 4 B's, and I got 500 C's just because that's a number I could do. Okay, let's look at the bottom. I canceled out that 0 there, so there's a 4. What's that in exponents? Well, 4 is 2 times 2, so it's 2 squared. Now I'm going to rewrite everything. A squared, B, C to the 499th. Boy, I bet that's really close to that 500. I bet there's something there, huh? All right. Okay, cool. Well, now we can actually do this. Everything's got exponents. Oh, what's happening? Can we keep seeing this on next class? Yeah, honestly, it depends on how far we get. I got 20 more slides for this unit. So yeah, no, you're gonna do a lot of exponents. We're gonna have fun with exponents. In fact, the next little header I got is exponents with exponents on them. It's gonna be fun. It's gonna be fine. And actually, this is actually a good example. I would actually see a problem like this in Math 126. That is college algebra. That is higher than the test you guys are aiming for. You already have all of the skills for this problem. Okay, so we got exponents. No problem. That light working? It's supposed to have a light on it. The light for the light was already on, but the light was not on. I hate this thing. I hate it and I love it. I can point it at the room and use it as a camera instead. Kind of funky. All right, so we're already ready to go. I hope I've rambled on long enough for everybody to write everything. So, this too, top power minus bottom power. All of these are kind of multiplied together, right? That's the implication with the variables. That are stuck up together. If they're stuck up together, it implies multiplication. So this implies that it's multiplied by A, it's multiplied by B, it's multiplied by C. just because they're kind of stuck up next to each other. So everything is going to be multiplied. Okay, let's look at the A's. Oh God, it's an A, it's a variable. Oh God, variables. What does that mean? It means it's a number, I don't know. Okay, so it's just an A. I don't care. But there's 6 on top and 2 on bottom, exactly the same as the 2's. Okay. I did not do that intentionally. Okay, but what about the B's? Well, I got 4 up top. That one doesn't have an exponent, but it's hanging out. So there's one of them there. So you'll have 4 minus 1. And then for the C's, I got 500 up here and 499 down here. So you have 500 minus 499. Then you just do the subtraction. Six minus 2, 4. It's going to be the same thing on the A. 6 minus 2, 4. And notice that I'm not putting my multiplication symbol in between because this is where I'm gonna be done. This is it. This is my 3-step giant ugly problem. Okay, B's. I got 4 minus 1, so there's 3 of them. And then C's, 500 of them minus 499 of them. Well, I got 1 left, so writing C is good enough. I don't have to write squared or cubed or anything because there's just 1 of them. Can I do anything with this? Can I clean it up? I mean, I might be able to multiply out 2 4 times, but I don't feel like it. Here we go. That's it. You just turn it into exponents and just do top power minus bottom power. Could have even split this up and done all these ugly variables in the first step, right? I could have immediately said, 6 minus 2, 4 minus 1, 500 minus 499. And this is why I told people that you get good at these things, you can just straight up look like a wizard. Because you can actually just look at this and say, hey, what's 64 divided by 4? Because, if you have 640 divided by 40, the zeros cancel. 64 divided by 4, that's 16. Okay, that subtraction, 4 of them, right? That subtraction, 4 minus 1, 3. That subtraction, 1. Cool, you're done. You can just do that in 1 step. Doesn't matter. Is it cheap? Yes, it's totally cheap. Exponents are cheap. They make you look like a wizard, but really all you're doing is just subtracting powers. So how are we feeling about this? Did I lose you guys with this? Did I scare you? Are you terrified? Do not fear letters. Letters are numbers you just don't know about yet. Yeah, see, it's not too bad, right? It's not the end of the world. It's just 7:30, which means I want to break until 7:40. And this seems like a good time to do it. So you're all free for 10 minutes. And then we'll do more exponents. And if you have any questions, throw them at the chat. I'll still be here. Okay, did everyone have a nice, fun, short break to remind you of what life is like without math? And then we're just gonna go straight back into it. You're all gonna be very happy about this. Yeah, cool, me too. So let's do some math. Things I want to scream at a cop sometime and see if he's like, what did you say? I meant math. I mean it. I have a book right here. Are you like that one correctional officer in El Dorado County that got caught on meth when he went into town, into work? Hear about that? That was awesome. There's actually a police officer who went to work in El Dorado County high on meth. So yeah, he's in trouble because that's stupid. That's so stupid. Okay, so now we have exponents with powers on them. So I'm missing a slide. That is not, that's not good. Where did the slide go? That isn't the first one for that. Technical difficulties, please stand by. Believe it or not, it didn't start with example number 2. Why am I missing a slide? Let's look at winter. Well, it seems that I accidentally deleted the slide when I went to make this semester's stuff. How did that happen? Oh my God, I'm just straight up missing it. It's been deleted from everything I have. Well, that's not good. Had I known this, I would have spent the last 10 minutes on that. Technical difficulties, please stand by. Huh. It just straight up disappeared. I have 3 places that slide's supposed to be, and it is missing from every single one of them. When in doubt, just completely plagiarize. Making this work. Image 0.png. I'm not okay with that. Technical difficulties, please stand by. Never had to panic like this. Hey, there we go. Everybody got a 16-minute break anyway. Oops. So this is not how I wanted to explain this, but how I wanted to explain it has apparently been deleted. So yeah, that's cool. So I made a random slide. Here we go. Did I just copy this from, the For Dummies website? I don't know what you're talking about. So exponents to a power. So if you look at Mr. Example down there at the bottom, that means that when you have an exponent or something with an exponent, if it's in parentheses and has an exponent outside of that set of parentheses, that is implying that you have 6 of every single thing inside, right? Well, if I have 6 of those x to the thirds, then I have those 3, that 3, 6 times. So you can kind of see that what ends up happening is you end up multiplying those powers. Anytime you have the situation where you have an exponent to another exponent like this, with an exponent on the outside, it just multiplies the powers together. At least I still have my example. So for example, if I have x, I really have something that close to the one I just randomly found on the internet and copied. Yes, I did. Yes, I did. Yes, I did. All right, so x squared in a set of parentheses to the 4th power. I'm going to kind of blow this up for everybody in class. You're going to have, those of you online are probably going to see some black squaring happening on the right. That is perfectly normal. You don't care what's going to be under there. That's just where I can see whether or not you guys are talking to me. Which I need a little bit more space. There we go. Okay. So x squared and that whole thing to the 4th power. So the 4th power is outside the set of parentheses. It's saying that you have that x squared multiplied by itself 4 times. So like that, middle line there, you have x squared, x squared, x squared, x squared. So like from the rules that we did earlier, if you have something like that happen, you would just add all the powers, right? 2 plus 2 plus 2 plus 2, you have 8 x's being multiplied together. So what you end up doing is, instead of looking at it that way, you would say, okay, well, how many times did I just have that 2? 4. So you could just multiply those powers. So if you look at the bottom row there, instead of x squared to the 4th power, you can actually just have it as x to the power of 2 times 4. Just multiply those numbers together, and you end up with the 8th power. Makes your life a lot easier, a lot easier. Now, the biggest thing that I see when people are learning these things with exponents is confusion and just confusing the 2 rules. I will see people mix up this rule with the one that we did in the last little section where we had, the power plus the power. So just keep in mind that it's multiplication if that power is on the outside of that set of parentheses. If that power is kind of attached to a whole term, that's when you multiply. But if you have the powers on each individual little term, that's when you can add them. So exactly what's happening on this slide with the middle row, that's when you end up adding the powers. But on the bottom row, you can see, okay, if the 4 is outside of the parentheses, that's multiplying. And don't worry, we're gonna do some examples. Let me be really cheap here for a moment, because I'm going to forget that I lost this slide. So I'm totally just editing this for next class. Cool. Yeah. I'm losing it. There we go. I totally just started editing and working out of the one from 3 months ago. It's cool. It's cool. We're good. We're good. We're not good. I just deleted the examples. There we go. We're good. I'm not losing it this time. There they are. I found it. Okay. So look at that. I got 3s and 2s everywhere. In fact, I'm gonna edit that a little bit because I don't want too many twos. Let's make this I don't know, let's make that a 5. Let's make that I don't know. Let's make that a 7. Let's make this one make it an 8. I don't care. Yeah, it's nice. I like that. That works better. Let's make that a 6. Okay. I don't know what my obsession was with second and third powers on this example setup. Okay. So for number 1, it's not too bad. We just have me trying to write a 1 and not my pen not working. We have 2 cubed, and that thing is to the 8th power. So that's telling us we have 8 of this thing. So on the inside, this one is telling us we have 3 of this 2. So I have 3 of that 2, 8 times. Well, if I have 3 of that 2, 8 times, that implies that I could just have that 2 3 times 8 times. You just multiply the powers. So the powers outside of the parentheses, you multiply. 3 times 8 is 24. We would not figure out what that is. I'm kind of curious. So I'm going to punch it in my calculator and see if I break it. Oh, okay, that's not too bad. 16,777,216. Yeah, no, normally I'd leave that alone. Leaving that alone. 2 to the 24th. That sounds great. We're not gonna worry about that any further. Okay, let's do more. That was nice. That was neat. That was simple. We have another nice, neat, simple one before we start getting into ugly ones that I put together for no good reason. All right. So we have 3 to the 7th to the 2nd power. So I have 7 of them twice. If I have 7 of them twice, then I have 14 of them. That's it. That's all we got to do. They're not bad. And remember, these are just building blocks. So these are rules you're going to have to be able to use whenever it is that we're working with exponents. So remember, these are usually just going to be a part of another problem. So in the future, you're going to see more things that are probably closer to Mr. Big Ugly back here. Mr. Big Ugly back here isn't too bad, but you know, if I put a set of parentheses in there and some extra, you know, extra multiplication and such, then it could be ugly. I want to do this section next. I don't want us to hit that quite yet. Cool. Next one, I'll write it down real quick. This is where you're going to start not liking me. Oh my God, look at those. Parentheses everywhere. Oh my God. We have 2 opening parentheses, 3 squared, close parentheses, 5th power, close parentheses, 2nd power. So the question I would pose to you guys is, can I just multiply all 3 of those together? Can I? Well, I haven't told you whether I can or not, right? So let's see what happens. Let's see what happens. If you get to something like this and you don't know how to proceed, you don't know what to do with this, right? If it was simpler, you'd know what to do. If it looked like this, right? Well, let's look at the part that does look like that. Let's look at that part. right? We can kind of just look at that part first. It's inside of these sets of parentheses, so we could do that, right? We can do that. So let's not worry about this part. Let's worry about everything inside, try to clean that up and see what happens. Okay, well, if I have something like this happen, we know that this is going to be multiplying the powers between these two, right? So we end up with 3 to the power of 2 times 5, just like the last problem. We're just doing the inside part. So we would have 3 to the 10th. Oh, but now it's something we can do, right? Now it's something we can do. Because now, don't ask me why I'm going down and then to the right. I don't know what's happening in my brain. This is just kind of how it maps out in my head. The topography of Ben's brain is weird and confusing. Okay, well now we can just do these multiplication wise, right? So we would have 3 to the 20th. Is that what we would have had if we multiplied all those numbers together? 2 times 5 is 10, times 2 is 20. So it actually would have worked out, right? Is there a specific rule for that? Not exactly. But you can kind of pull that from what happens here. If I have a power on the outside, it multiplies by the power on the inside. Well, what's the power on the inside? Well, this power times that, right? Essentially what's happening is you have, and kind of bring it over here. Essentially what you have is that 2 and 5 being multiplied together and then having another 2 on the outside, right? And that ended up working out quite nicely because we got that, right? That's exactly where we ended up. But you can kind of work these things out and see those types of things happening. No shortcut for this? Well, there kind of is a shortcut. That's what I'm saying. You can see from how we did this that these 3 powers are getting multiplied together, right? Right? That's what ends up happening. So if I end up having a problem like exactly like this, do I do this again to you? No, I don't. Okay. If I run into this exactly the same way, this is how I would work this out. Because if I threw this at you and I asked you again, do all of the powers multiply together? You can say yes now because we just proved that that's what ends up happening. But would you have been sure of it right here? No. So if you're not sure of something, chop it up into little baby steps. Do little baby steps and then worry about the bigger picture. So yeah, you can kind of see that as a shortcut that we just proved that works that way. But I can also point out that this is more of like a thought process one I did you. You're never really going to see this in a math book. You're not going to be expected to do a power. You're just not. But you ever do a math exercise in school and say, why the hell are they giving me this type of problem? I'm never going to see it this way, because they want you to understand what's happening. That's really it. That's what I'm really wanting to show you guys. If you understand that the powers are being multiplied right here, that is beautiful. That is what I'm aiming for. Let's do some ugly ones. And by ugly ones, I just mean this one's got variables. Kind of reminds you of part of that big ugly one I did earlier, right? We got a squared and b to the 5th inside of a set of parentheses, and that whole thing has a 10th power. This is more similar to something that you'll see in like like the higher end of Math 96, maybe Math 126. When you're doing the actual like college level math stuff with exponents, this is part of what you'll see. You'll see these types of things in equations. And by then you won't be terrified of them. They'll just be, I got some stuff with powers on it, whoop-de-doo. What am I gonna do with it? Well, we know what to do when we have one thing. What do I do with when I have two things? Well, let's try to wrap our heads around this. Let's look at what we've covered so far. What have we covered that has two things? Oh, we did this one. That has two things. Let's see what happened here. What did we do here? Well, the rules applied the same. We just looked at each part separately, right? Well, what's happening back here? Well, we got two things multiplied together. Wouldn't it make sense if we did both of them separately, but they kind of ended up together? Yeah, exactly. That is exactly what happens. When you have multiple things in here with the power, I almost said multiple terms, but technically you have a term anytime you have two things or you have one like cohesive product. Like, you're not gonna like it, but this whole thing is a term because it cleans up to a term. But if I had like a plus or a minus between these, if I had a plus right here, then I would have a term plus a term. Right here, since they're multiplied together, it's just a thing, right? How do I deal with this ugly thing? Well, this power actually is just going to distribute. It applies to each of these separately. Both of these are to the 10th power. So what happens on each one separately? You end up multiplying those powers. If I had a squared and then with a 10 on the outside, I would have a to the 2 times 10, right? Same with b. I would have a b with a 5 on the inside and then 10 on the outside. That's going to imply that they multiply together. The powers multiply together. So you end up doing the same thing. It just kind of ends up hitting each piece. The pieces don't interact with each other, but you know, they're still multiplied together. So we keep them kind of smushed. That is absolutely the technical term, smushed. It has to be, because I don't know a better word for it. And that's it. We just multiplied both of those by 10. That's it. That is it. Now you might say, Ben, what do I do if there was a plus between those? You don't want to know. You do not, absolutely do not want to know right now. I would not want to do that problem myself. I would hate it. It turns into this giant, weird, hideous binomial theorem thing, and you end up with a pyramid, upside down pyramid of numbers, and just, God, putting a 10 on that. I don't hate anyone enough to do that to them. I don't. But that is something we're not going to cover in class. But something like that, oh yeah, you're going to see that a lot. And more likely it'll be like an x plus 2 or something funky like that. Are you going to see that on the high set? Probably not. Probably not. I haven't seen anything like that in any of the practice material, but that is where exponents will eventually take you. Let's do one more of these guys, and then I'll show you something else that's fancy. Oh man, this one looks awful lot like one of those problems that I did earlier, doesn't it? Oh my goodness. So we have big ugly parentheses. Inside big ugly parentheses, we have 5 squared times 25. And that whole big ugly parentheses is to the power of 6. And yes, this is, the inside here is identical to a problem we did earlier. because what do I do with this thing? What do I do? Where do I start? Where do I start? That's really the best question, right? You get something like this, you don't know what you're doing. Where do you start? Usually the answer is the furthest in that you can go. And by that, I mean the furthest inside parentheses. The most basic part of this that you can look at is this 25. What's happening with this 25? Well, not a whole lot is happening inside these parentheses, right? So we have to start looking at the picture further outside of it. Well, we have a thing outside of the parentheses. If I have something outside of the parentheses, that implies this is multiplying onto that. Okay, so this is multiplying onto that. And again, we're just gonna kind of bring down the outside stuff. Less worried about that, more worried about what's happening inside here, right? So we're doing everything with powers. So chances are we're going to take this 25, we're going to turn it into an exponent. 25 is 5 squared, so now we have that. Okay. All right. Well, it almost looks uglier because now I got another exponent, but again, we're kind of working our way outwards from that parentheses, right? So now if I have to multiply this onto there, aha, I have 5 squared times 5 squared. I have 2 5s multiplied onto 2 5s. So how many 5s do I have multiplied together? That's where we add the powers. I'm going to do this as an intermediate step right here that we can see that we're adding these powers. If you are working it on your own and you can see that you're just going to add those powers and you just want to jump into doing it that way, absolutely. You can absolutely jump to the point where you've already added these powers and put 5 to the 4th. I'm not going to because I don't like skipping steps. And I imagine you guys don't want me to skip any steps because that would be a jerk move. I remember having teachers that would skip steps and it's like, this is all the algebra stuff. You know this stuff by now. I'm like, yeah, but my brain is goo because you're hurting it. Please just give me every intermediate stupid thing so that I don't get lost. Well, we've broken this down pretty far. All I have on the inside is 5 to the 4th. Cool, we know how to deal with that. We have a power on the outside. That means we're going to multiply by the power on the inside.
I have a question.
Yeah.
How we ended up with the 5 2 on the second?
This guy?
Yeah.
By breaking this guy down, we broke it down into an exponent. So you can kind of, if you need to, we can break it down with a little tree diagram. We don't need to because it's just 25, but we know that 25 is 5 times 5, which would imply that that is 5 squared. So we just turned this guy into an exponent, kind of like what we were doing earlier. And like I've said before, everything you do with math tends to build on each other. We had a whole little section where we were doing just breaking this guy into an exponential, right? We did a couple of them at the beginning. What do? Well, now it's just a piece of a problem. All those pieces will eventually go together to make some horrible mishmash thing that you never want to see in your life, but you're gonna. So again, we converted this 25 to a 5 squared, just so we could put it together with this guy. Otherwise, we would have had to do 25 times 25, and that just wouldn't have made my day nice. I think 25 times 25 is 625, and bringing that to the 6th power would just make me want to hit my head on the wall until I fell asleep. I don't want to do that. Working these with exponents lets us avoid giant, horrible numbers like, let's see, 5 to the 24th. Normally, my calculator can handle giant, horrible numbers like that. That is a very giant, horrible number. Look at that thing. We were not at any point doing numbers to that order. In fact, most calculators aren't going to give you a number like that. It's just going to spit out something with a little e and then have a number after it, and you're gonna be like, what does this mean? And I'm gonna be like, cool, you're gonna learn that next class. Don't worry about it now. So yeah. Yeah, you don't want to do 5 to the 24th. You do not want to do this math without exponents, because you will end up with, I don't know what number that is. I don't know. What is that? Is it gonna be nice? 1, 2, 3. 1, 2, 3. So that's okay. So this is the millions. So okay, so that's billions. So that's trillions. What's after trillion? Because I don't know what that is, but it's 59 and change of that. we don't want to do that, right? Yeah, it's a big freaking number. That is so big, it makes Elon's bank account look like toys. That makes Elon's bank account looks like buying a Snickers at the supermarket. That's how big that number is. Also, his bank account doesn't look like that. His bank account looks very small, and he has all his money in stocks, so he can, you don't have to pay for what you taxes on what you have in the stock market. You have to pay taxes on what you pull out of the stock market. All of his money's in stocks, so he doesn't have to pay taxes. I paid more taxes last year than most billionaires combined. I don't like that. I don't like that. But you know what? They're rich enough to figure out tax havens. I think I should write a book about making tax havens for the rest of us. But I gotta figure that stuff out too, because again, I paid more than all of them combined. All right. Cool. So that finishes us off for exponents with exponents. We got enough time to at least look at the next stuff. Next stuff isn't too bad. The next stuff is, well, it's kind of weird. It's kind of weird, not gonna lie. Negative exponents. It's when you have a power with a negative on it. What the heck? So to understand negative exponents, we kind of have to examine what an exponent is, right? I mean, before we think of the negative on that thing, think about what it is that power means. That power means I have that thing multiplied by itself that many times. And then if we start pulling together all of these ones with different powers on them, with the same base, we start adding them together, right? So what happens when we have a minus? Well, if we have a minus, it kind of means the opposite, right? Instead of multiplying all of them together, it means that we're kind of dividing them all together, which is kind of awkward. It basically pushes them into all of them being divided, which ends up with all of them multiplying together in the bottom of a fraction. So let's look at that a little bit more. Yeah?
Yeah, I missed this section.
Immediate, like, what the hell is this? Cool. They're not bad. They're not bad. They're on par with learning all this other stuff. And actually, I would actually say that with that previous big ugly example with algebra in it, I showed people in like 126, because this pulls in with that. I showed them how to cancel things with that, and you could do all of it in one step, just after understanding all of this stuff. It's great. So how do you make this work for us? 2 to the negative third is dividing, but how? So what you end up doing is you end up considering them as their reciprocals instead. So if I have 2 to the negative third, that is equivalent to 1 over 2 to the third. It ends up kind of flipping. If I have a negative power, it'll just flip to the bottom and become positive. And it actually works both ways. If I have a negative power in the bottom of a fraction, it can actually flip to the top of the fraction and become positive. So it's kind of awkward to wrap your head around, but they're basically like, it's kind of like inverses. They're kind of inverses of those numbers. So 2 to the negative third, you would just change it. You would flip it into a fraction and call it 1 over 2 to the third. Looking at that last paragraph there, 1 over 5 to the negative second, right here, 1 over 5 to the negative second, it would do the same thing, but it would go from the bottom to the top. So it would become 5 to the second over 1, and then you don't really have to have, you don't really have to have it over 1. 5 squared is 25. So it actually works out quite nicely. So let's wrap our heads around these.
Are you gonna start off with this next class?
Do you need to run?
No.
Okay. I mean, I got 8 of these and I'm not gonna finish them in 12 minutes. So yes. Either way, I'm gonna cover everything that we covered in this class in a review for the next class. So let's just look at these. And actually, I probably can do all of these in the next 12 minutes, or my pen's just gonna stop writing. Did I just run out of ink? That actually might be the case. I don't think I have a backup. Oh, you bitch. You guys can't see us. You guys can't see this. But holding this up to the light, it's just empty. This is the moment I ran out of ink. This is the moment.
Oh, it's a sign.
It is a sign. Oh, no, you didn't.
Testing.
Keep having another one on Chloe.
I mean, it's got ink. It's just, you know, hideous. Yeah. Hello, little fella. Yeah. Yeah. That one doesn't want to write. Let's try this one. Let's see what happens. Wait. Yeah, that's erasable. Okay, cool. I don't want to be out $30. Testing. No, that cartridge just sucks. Oh, wait. Nope. Nope, that cartridge just sucks. Okay, class is over. Oh. Oh my God.
So we'll start off with this.
Yeah, we're totally gonna start off with this next time, yeah. And by start off with this, I mean, you know, after I review everything else that I just covered. So, I don't know, 6:37, you know, sometime
So-
Tuesday.
Negative exponents.
Negative exponents, that's number 1 on the list for next class. I am out of ink. I am out of ink. Hey, look, another pen. Oh, come on, dude. It literally does just. What is happening right now?
You broke.
What is happening? All right, yes, this is legitimately a sign. You are all free. I don't think I can mess with fate to make that happen all at once. This is a multi-pen. There are straight up three types of ink in this. See, these are brand new cartridges too. This is a brand new pen. Wait, oh. Okay, that just sucks. All right. Yeah, no. All right, cool. Yep, you're all free. All right.
Have yourself a good weekend.
You guys have a great one. I hope you all have a wonderful evening. Enjoy your night. I'm going to scan these notes and then go home. Good night, all.
Watch the movie.
Huh?
Did you watch Doctor Strange or no?
No.